Hello and welcome to part 2 of this video series. In this video, video 2, we will be putting some numbers to the expressions that I derived in video 1 of this video series. So I would suggest watching video 1 before watching this video. On video 1, we derived expressions that can be solved for bubble pressure and bubble temperature for um, a liquid mixture, and also due pressure and due temperature for a vapor mixture. So first here, we're going to start. I have imported here some pre-written code. I've talked about this in recent videos that I've made for past homework problems for this class, but essentially what this is it's pre-written code that allows us to grab properties from a wide variety of different chemical compounds so that we don't have to, say for instance, type in the vapor pressure, the pure component vapor pressure of, let's say, benzene, and have to manually type it in. This allows us to just say, hey, we want that for benzene, and code it in to our code here. Some other things we have NumPy numerical Python. We have imported the root function because we will have to solve a equation here in a minute by using the root function. I've imported CHE as CHE for the CHE tools so that it's just simpler to type. Then I have these plotting tools down here, which we will use in the second part of this video. So to start here, what I'm going to do is I'm just going to define a variable here, p, so that this will allow us to grab the properties of the compounds that we're working with, which is benzene. This needs to be in quotes here. So benzene, and also um, toluene, because those are the two compounds that are in our mixtures. Again, I went over the problem statement in video 1, but yeah, these are the mixtures here, or the compounds in our mixture. Uh, so I'm just going to press shift enter there. And so first here, if we want to code in our expression here for the bubble pressure, if we want to start with the bubble pressure here. So what we'll need to do here is obviously define a function um, for our bubble pressure. So bubble pressure, or bubble P, I'll call it. And what we need to supply for our bubble pressure calculation, if you remember, we are given the temperature here in this case. Well, we're also given X, which is our the mole fraction in the liquid phase. So we have X, and we also have temperature that we're given. And here, for our bubble pressure calculation, if you'll remember, so what we're going to do here is we'll just return it right off the bat here, because we don't have, in the second calculation here for bubble temperature, it's a little bit more complicated. But here all we have to do is uh, return the sum, so np.sum of x, so the mole fraction of the liquid phase, and this is multiplied by p.pvap, and this here is the pure component vapor pressure here, if you remember. So we have our um, liquid phase mole fraction here and the pure component vapor pressure, which is dependent upon temperature. Okay, so let's go ahead and run that and make sure it runs. And we can go ahead and type, we can type our function out here, and if we give it, um, our liquid phase mole fractions here, so I'm going to have to give it in an array, or actually what I'm going to do here is if I add in a line of code, I'm going to go up here, and I'm going to set x equal to an array, so np.array, and it will be 0.3 first, because that is the um, it's 0.3 benzene and 0.7 toluene. So we'll go in order there. And I don't need this here. Okay. So that should run. Let's run this one more time. And what I can do here, since I have this set here, is I can supply X. And if we give a temperature of 323 kelvins here, for example, this will give us the bubble pressure here, this 192.90. Okay, so I'm going to go ahead and delete this here, and we can go ahead forward with our bubble temperature calculation here. So again, we'll have to define our bubble temperature function here. So bubble T, and this time what we are given, we still have the mole fraction in the liquid phase here, X, but this time for this calculation, we are given pressure here. So we have pressure, and this calculation is a little bit different. Uh, if you'll remember, in order to find out the temperature that the first bubble will form, what we need to do is have the partial pressures inside our container equal the pressure that we're given. So this P here, and at that moment, that's when the first vapor bubble will form. So we'll also need to define a function here, and we're basically going to um, how do I word this? We're going to define an equation here, and that equation we're ultimately going to drive to zero with the root solver so that we can find that temperature. So if I just define an equation here, and that's going to take in a vector, okay? And since this answer is going to be a vector, we're going to go ahead and grab the first component of that vector there. So the vector in this in bracket 0 will just allow us to grab the first component. And what we'll want to return here is we will want to return that equation that we want to drive to 0. So it'll need to be in brackets here. And the equation here will be bubble P, and we'll have to give it at X and let's see here, X and T, put a space there. And what we'll do here is we'll subtract the pressure that we're given, because if this, what we want here is this equation here to be driven to 0. So if this equation is driven to 0, it will give us the value here for our temperature. So what we'll do here on the outside, I think we're lined up there, is we'll go ahead and return, if I can write this, oops, return root, and we'll have our equation here first, and then we will have to obviously supply an initial guess. So let's just say 298 here. Okay, and if we want to go ahead and grab it, we can do .x. So I'm just going to go ahead and do that. And let's make sure it ran okay. So if I do bubble T, have X again, except this time, let's say, if you'll remember, we had, I believe it was 1, 2, let me see this here. So if we had bubble T, or bubble P, excuse me, our bubble pressure, we supplied 323 here. And let's make sure they match up here so that we know we're right. So we have 19290, okay? So let's go ahead and type in our bubble T, and we'll still have our 0.3 mole fraction of benzene, 0.7 mole fraction of toluene. And what we're going to do here is if we supply 19290, this should give us our 323 kelvins. So there we go. It's approximately 323. So that way we can just kind of verify that our calculation is correct here. But yeah, that we now have functions here that will allow us to calculate the bubble pressure when we know the temperature, and calculate the bubble temperature if we know the pressure. So now we can go ahead and talk about dew pressure and dew temperature. So I'll go ahead and start with the easier one of the two, dew pressure. So I'll go ahead and define a function here, dew P for our dew pressure. And if you remember, in a dew pressure and dew temperature situation, instead of having a liquid mixture, we have a vapor mixture. And in this case, when we're trying to calculate the dew pressure here, we're looking for the pressure when that first liquid drop forms from the vapor mixture. So here, instead of knowing X, the mole fraction in the liquid phase, we know Y, the mole fraction in the vapor phase, because that's what we're starting with. And we'll also know our temperature here. That'll be given because it's a dew pressure calculation. And what we'll be returning here, if you remember, we just have one expression here for our dew pressure, and that is 1 divided by the sum of y, our mole fraction in the vapor phase, divided by the pure component vapor pressure. So we'll go ahead and return that. So have 1 divided by np dot sum of y divided by p dot, that's p dot p vap, and of course this is dependent upon temperature here. So let's go ahead and run this. And what I'm going to do here is I'm going to go ahead and compare our bubble pressure and dew pressure just to see what's going on and what the relationship between the two is, if there is any at all. So I'm just going to set a temperature here, and I want to set it at 120 Kelvin. So I'm going to add 273.15 and 120 here, so that I have this in kelvins. So if we look at our bubble pressure here, so bubble P, and we'll have X, and we'll have to supply our temperature here, but since I already have this written out, we can just put T in there, and what we get is 181,656 here. So if I go ahead and look at our dew pressure, and let me go ahead, I'm actually going to add in a line of code here and go up to where our X is, and I'm going to add in our Y just because, so the code looks a bit organized here. So Y is obviously going to be the exact same as X. It's just that it's Y is the mole fraction in the vapor phase. So I'm going to go ahead and set that, run all these to make sure we're good. Okay, so for our dew pressure, we'll have a Y here, which is this, which is the same values as X, but a completely different concept. And we'll supply our temperature again and see what we get. And if you'll notice here, we have a different value here for our bubble pressure and our dew pressure. And this is the case because here we're working with a mixture. We have a mixture of benzene and toluene. If we were working with just one component, like let's say water, this would not be the case. But since we have a mixture here, it's just interesting to see that while you may think that they're the same, these values are definitely not the same. So what we can do here is now look at our dew temperature. So if I define a function here for our dew temperature, this here will still, again, we will know Y, and except this time we'll know pressure. We will be given the pressure, and we're looking for the temperature for when that first liquid drop forms. So similarly to the bubble temperature calculation, we're going to have to drive an equation to 0 and use the root solver in order to find our temperature here. So if we look here at this equation here is equal to the dew pressure, which is equal to pressure. So what we will need to do here is subtract pressure from the dew pressure in order to drive that equation to 0. And to do that, we'll use the root solver here. So what we're going to do here is define another equation here. And this will take in a vector just like the last one. And we will want to set temperature here equal to the first item in that vector. So we can grab that so that our code just looks cleaner, so we don't have to manually type it in. And here what we're going to return is our equation that we're driving to 0. So we will return dew pressure, again subtracting from that pressure so that we can drive it to 0, because those two are equal to each other. So dew pressure, and we will have Y and T, and we will subtract P here. Okay, oops. Okay, oops, get my bracket there. And on the outside here, what we're going to return is our root here, so that we can drive this expression here to 0 so that we can solve for the correct temperature here. So we'll have to have our equation here, and we'll have to have an initial guess. And again, we'll just guess 298 kelvins. I'm going to go ahead and put .x so we can just grab that solution here. And let's make sure this runs okay. I don't think I had any errors here. So let's go ahead, and if we look at due temperature, we'll have y. And if we guess here a pressure of 157,733, again, just like the bubble pressure and bubble temperature calculation, they should match up, and that makes sense if we think about it logically. So let's put in 157,733, and we should get, yep, 393 kelvins. So now we know we have correctly calculated here. We basically verified for our bubble pressure and bubble temperature, and also our due temperature and our due pressure here. So one last thing here that I actually forgot to do earlier is we're getting a two-component array here. So what I'm going to do is just grab the actual value from this. So if we do dot 0, it should work there. Whoops. Well, it's not too important. Let's see here. If we grab it, dot 0. Okay. So it looks like it's working there. I'm not sure if it's working correctly here, but now since we've calculated this, we can go ahead and move on to the second part of this video.
So for the second part of this video, we're asked to generate two plots for the binary vapor-liquid equilibrium phase at both a constant temperature of 393 Kelvin and a constant pressure of 150 kilopascals. So in order to do this, what we will have here on the x-axis is x1. So we will be plotting the more volatile component on the x-axis here. So x1 denotes the mole fraction here for benzene. Remember, we have 1 as benzene, which is the more volatile component of the mixture, and 2 is toluene. So for here, since we know the temperature here, what we're going to plot on the y-axis here is pressure. And here, since we know the pressure here, we will be plotting temperature. So if we look here at this first plot here, we are going to look at x1 here, and we'll be going from 0 to 1. Because x1, the mole fractions can't add up to be something greater than 1, and they obviously can't be less than 0. So if we look here at x1, well, when x1 is 0, so when there's no benzene present and it's all toluene, what is the vapor pressure here going to be? Well, we can't give an exact number right now here. When we actually plot this in Python here, we will actually get an exact number here. But just looking at it generically, we can say that we'll have a point here, let's say, and let's say we have x1 at 1 here. So we have pure benzene and no toluene present. Well, what we're going to see here is that we're going to have a point up here, because the vapor pressure here, if we have pure toluene, we're going to have a lower point because the vapor pressure of toluene is less than that of benzene. And here at 1, for x1, remember we're plotting x1 on the x-axis. If we have pure benzene here, we're going to have a higher vapor pressure because the vapor pressure of benzene is higher than that of toluene. So now what we're going to look at is we're going to have two curves on this plot here. And what we're going to see is we're going to have the liquid on the top, and we're going to have the vapor on the bottom. And this makes sense here because if we condense here, we're going to form a liquid here if we raise the pressure here. So if you want to think of it something like this, this is what our plot will look like once we generate these plots in Python. And that makes sense going through again with the points here. Uh, if you just looked at this first glance, you may have no idea what's going on, but you really have to take it step by step to fully understand what's going on. So let's go ahead and go into Python, and we can sort of set up a basis that will allow us to plot some linearly spaced points here and get our curves.
So the first thing that we're going to do here is we're going to plot our bubble pressures first. So what I'm going to do here is linearly space out our x1 points on the x-axis. So we'll have x1 equals np dot linspace. We'll have them going from 0 to 1, obviously, because we can't be less than 0 and greater than 1. And we'll go ahead and plot 11 different points. And we can go ahead and say here that x2 is 1 minus x1. So we'll go x2 equals 1 minus x1. And I'm also going to go ahead and supply our temperature here of 393 Kelvin. So if I go 273.15, or actually I'll just hard code it in as 393. Or I guess I'll go ahead and add it in. So 273.15 plus 120 just to keep it consistent with what we're doing. So now what we want to go ahead and do is add together our bubble pressure list for both our benzene and toluene, our two different components here. So what I'm going to do here is first add a variable psat, and I'm going to set this equal to the pure component vapor pressures at the temperature that we're given so that we can more easily write our code for the bubble pressure list that we want to plot. So if I do psat, let's see here, psat equals p dot pvap, again, pure component vapor pressure at the temperature that we supply here. And here we can go ahead and make our bubble pressure list to be able to plot it. So we need a different variable than our bubble p because we don't want those two to, they obviously have to be different here. So our bubble pressure, we'll do bubble p list. And here what we're going to do is we're going to add the bubble pressures here for both components, so x1 and x2. So if we have x1, and if you remember, the bubble pressure is the mole fraction in the liquid phase times the pure component vapor pressure. And what we're going to do is multiply both of those for each component and add them up. So x1 times psat. And for our psat here, we want to grab the first value in this list for x1. And if we go up here, we have that as benzene. So we'll go ahead and grab that, and we'll add x2 times its pure component vapor pressure, and that will be 1 there for x2. And let's go ahead and make sure that runs. Okay, so let's go ahead and plot up our bubble pressure list here. So if we go fig equals make subplots, and we're going to want to have, again, our two different plots here. So we'll have one row, however, we'll have two columns for the two different plots. So we'll have rows equal 1 and columns equal to 2. Okay, and we'll go ahead and add our scatter plot for the bubble P list here. So if we do fig.add scatter, we'll have x equal to x1 because that's what we want on our x-axis. On our y-axis, we will want our bubble pressure list because, again, this is the one we're plotting at a constant temperature of 393. So on our y-axis will be pressure. So bubble P list. And we'll go ahead and set this on the first row and the first column. And I think I'm good here. Let's go ahead and plot it up. And this is what it looks like here for our bubble pressure curve. And this would make sense that we have a linear straight line like this because the bubble pressure is equal to the mole fraction in each phase. So xi times the pure component vapor pressure for each of the components. So now what we'll want to go ahead and do is plot up our dew pressure. So what we're going to need to do here in order to plot our dew pressure list here, if we go up and look at dew pressure here, let's see where, here it is. So we have our dew pressure calculation here. And what we're essentially going to need to do is we're going to create an empty list here for our dew pressure list. And we're going to need a for loop in order to continuously call this function in to be able to add to our dew pressure list. So let me go down here and I'm going to go ahead and add in, I'm going to add in a line of code right in here. And I'm going to go and create do p list. And like I said, I'm going to create it as an empty list here, and we're going to go ahead and create a for loop. So what I'm going to do is, since for a dew pressure, we're talking about the, instead of x1, we're talking about y1, which is the mole fraction of the vapor phase, since we would be starting from all vapor. I'm going to go ahead and change our x's here into whoops. I'm going to go ahead and change our x's here into z so that we can just keep the same values here because they're all the same values for x and y. So I'm just going to change it to one common variable name here. So we have x here. I'm going to change this to z, z again, and z. So what I'm going to do here is I'm going to say for y1 and z1. So we're going to continuously take this step by step. So for y1 and z1, well, z1 is linearly spaced out 0 to 1 with 11 points. So that will allow us to iterate step by step here. And what I'm going to do here is we can just say our y2 is just simply 1 minus y1. So 1 minus y1 to give us our toluene values there. And what I'm going to do here is to type in our y. Our y here is an array. So what I'm going to do is I'm going to add this in as an array. So np array, and have both, excuse me, that should be a bracket, yep. And we'll have both y1 and y2, so we can add this in as a 2-column array here with both of the values side by side. So we'll have benzene, and then we'll have toluene side by side. So if we have y1 and y2 there, and what we'll need to do here is just go ahead and append onto our dew pressure list our, let's go up here, our calculation here for our dew pressure when we have obviously the mole fraction y and the temperature T here. So what I'm going to do is go ahead and just add that. So do p list, and dot append is just to add continuously in this for loop to our dew pressure list. So we're going to append our calculation here. So do p at y and t, and let's go ahead and make sure this runs. And now we can go ahead and run these other here. Oh, let's see here. Oh, we need to run our z there. So let's go ahead and I can just copy this down, and I can add our dew pressure list this time instead of our bubble pressure. So if we have dew pressure, and we still have, again, since we changed this to z here, we don't have to worry about putting x1 and y1. It's the same values. We're going from 0 to 1 spaced out evenly. So I have our dew pressure list. I believe that's a lowercase p. Yeah, lowercase p. So let's go ahead and plot it and make sure it comes up okay. So yep. So this is our first plot here. So when we have a constant temperature here of 393 Kelvin, and when I'm finished with these plots here, I'll go ahead and add a graph label and even maybe some axis labels here. But what this is telling us is that if we're starting from all liquid here and we decrease the pressure, this here is the temperature here when the first drop forms. And similarly, if we look when we start from all vapor, or excuse me, this would be not the first drop forms, but the first bubble. And if we look here, if we start from all vapor and we increase the pressure, this red dew pressure line would be the temperature here when that first liquid drop forms. So that will wrap up our first graph here. And like I said, at the end, when I plot our second here, I'll go ahead and make these look pretty and label them just so it looks a little bit nicer. So I went ahead and made a couple changes here to our plot. First, I just added names for our curves here, so bubble P and dew P. So we have our bubble P curve here in the blue and our dew pressure curve here in the red. I also updated the y-axis just so that we remember we have pressure on the y-axis when we are given a constant temperature here. And after we plot the second one, I'll also put temperature on the y-axis of our second plot. And then I just gave both of our plots here an overall title of binary vapor-liquid equilibrium for our compound 1, which is benzene, and compound 2, which is toluene. So if we want to go ahead and plot up our second plot here, before we do that, if we just think logically to think about what this may look like, well, if we have given a pressure here and we have temperature on the y-axis, if we have again x1 on the x-axis, where's the dot going to be on 1 relative to the dot on when we have 0 for x1? Well, if we think about it, when x1 is 1, that means we have pure benzene. So we are going to have a lower dot comparatively to toluene because benzene is the more volatile component. So we need we need to raise the temperature less in order to have that first drop to form. Um, and when we have x1 at 0, we're going to have a dot higher because toluene is the less volatile component. And when x1 is 0, that means we have pure toluene. So that's just thinking about it logically, what it'll look like before we plot it. So in order to plot it, what we're going to do is something similar here to our dew pressure list. We're going to run our bubble temperature and our dew temperature through a for loop and essentially add on to that list the components that we need. So let me add a line of code here. And we're going to do this in one for loop here, both of the lists. So what I'm going to do here is we do bubble temperature. So bubble T list, again creating an empty list, and we'll have dew T list, again an empty list, and we'll have our for loop here, except this time, since we're dealing with both x, the mole fraction of the liquid phase, and y, the mole fraction in the vapor phase, so we don't get our variable names here confused within Python. What I'm going to do here is instead of using x1, I'll use xy1. So same thing, we want them linearly spaced out. We already have z1 here, so we'll have xy1 in z1. Okay, put our colon there. And we can go ahead and write our xy2 equals 1 minus xy1. So xy2 equals 1 minus xy1. Okay. And what we will want to do here is go ahead and append onto our list. So last time I went ahead and I added our components in this way. However, this time what I'm going to do is add it in a different way. So if I go down here, I'm going to add first to our bubble temperature list. So bubble T list should be a lowercase l dot append. Oops. And what we're going to add here, again, if we go up here, we have our bubble temperature calculation. So we are going to add our bubble temperature calculation. So we will have bubble T, and adding our x1 and y1 components in this way. We can go up here and look at how we did it this way, and we'll just add the same exact thing in. So bubble temperature will have an array, and we'll have x1 comma x2. Okay, and we will also, whoops, that should be after here. We should supply our temperature here, or our pressure here, excuse me. Um, so instead of manually coding it in here, since we have a constant temperature for both of these, instead of typing it in twice, I'm just going to add a variable name here. So P equals 150,000 pascals or 150 kilopascals. Okay, yep. Okay, bubble T list. And it looks like our parentheses match up, so we should be good. And I'm going to go ahead and add on to our do temperature list here. So do T list dot append. Excuse me, this should be xy1. xy. Forgot we had to change it there. Okay, so append, and except this time we're going to have our due temperature. So if we scroll up here, we have our due temperature calculation here. And again, we'll have xy1 and xy2, and we'll have to supply our pressure. And like I said, since we're doing it twice, I just created a variable named p for it here. So I have an array, np dot array, open parentheses, xy1 and xy2. Okay, and after we will need to supply our pressure. Okay, so let's go ahead and make sure this runs. And what I'm going to do here is we're going to go ahead and add in, I'm just going to copy and paste here. So make it a bit quicker so I'm not spending too much time on formatting here. Except this time we'll have our, we'll plot our bubble temperature first. Bubble T list. And we'll have it in the second column. And the name will make bubble, or yeah, that's right, bubble T. Let's make sure this plots first. Okay, yep. So that plots okay. And here. Oh, whoops. I did not mean to do that. It should be bubble P or bubble T list. And this will be, excuse me, bubble T. End quote. Oh, it should be column 2. Sorry about that. I had tried to copy it and accidentally clicked paste. So if we paste this and our y here, instead of having our bubble T, we'll have our do T. So do T list our due temperature here, and we'll have do here. Okay, so there we go. And just to logically again go through this graph, what we're going to have here, it's going to be the opposite here. So we're actually going to have liquid here on the bottom and vapor on the top. So these are our two curves here at a constant pressure. And again, we have this labeled over here, but I'm going to go in and add a few formatting things. But I'm going to skip through that just because it's taking me quite a bit of time here just for the formatting. Okay, so I just went ahead and added a few things here. The first thing I added was up here. I added I updated our y-axis title for our second graph, so column 2 to be our temperature, since that's what we're plotting on our y-axis since we know our pressure in this case. I also added some tick values down here from 0 to 1, spaced out with 11 points. And how I did that was you have to obviously update the x-axis, and if you use this function tick vols and then linearly space out the points to your liking, that will allow us to get the points here that we have on our x-axis. And then lastly, I just changed the names of our x-axis. Since we're dealing with here our due pressure curve and our bubble pressure curve, technically we're plotting x1 and y1 because we have mole fraction of the liquid phase and mole fraction of the vapor phase. So just to be more clear there. But yeah, this will wrap up this video. And just to give a recap here, this is our due pressure here. So basically we're starting from vapor down here and we're saying, okay, what do we need to raise the pressure to if we know our temperature in order to have that first liquid drop form? And up here, we're starting from liquid, and when we decrease the pressure, we're looking, this line here is when that first bubble forms. And over here to the right, it is the complete opposite. See, we have our bubble temperature down here. So here, down here, we're starting from all liquid, and we're saying, okay, if we raise the temperature, if we know the pressure, uh, at what temperature will we need to raise to in order for that first vapor um, bubble to form? And up here in the top right, that's when we would have our, well, this purple curve here is our due temperature curve. So that's obviously when we have our vapor. And what we're looking for here is what do we need to cool this system down to or decrease the temperature to have that first liquid drop forms. So that'll wrap up part 2 of this video series. In part 3, we're going to be looking at what if we have a point here that lies in between. So let's say we have a point that lies in between our due temperature and our bubble temperature curve here. What we're going to have is we're going to have both a vapor and a liquid aspect of our component there, and we're going to look at how much do we have of each and what are the compositions of each phase. So that's what we'll be looking at in part 3.